familiar to you, okay, because we talked about, all right, the anatomy of the thyroid gland in lab class last Wednesday, okay? So we were introduced to it last semester in 210 when we were doing the general body plan. And if you look at the thyroid gland, I'm going to skip to this slide, I'll come right back. All right, it looks like, it's described, to me, it looks like the letter H. It's also described as a butterfly, okay? But it's going to have that kind of configuration. You can see it a little bit better over here, okay? Located right below or inferior to the thyroid cartilage, all right? And it is connected, it has two lobes, the right and the left, and then it's connected in the center by the isthmus, all right? And as you saw here, check it out. Look at all these blood vessels. So it's highly vascularized. Makes sense, right? Because our circulatory system is kind of like our transport system, all right? It's going to, since we're talking about the endocrine system, and the endocrine system are ductless glands. So when these glands are producing whatever the secretion or hormone that they're making, we've got to get it into the body somewhere and circulate it throughout. The best way to do that is through the circulatory system, okay? So it's highly vascularized, so these cells will secrete their hormones directly into the blood vessels here so they can have systemic circulation within moments, okay? So the predominant cell types that we're really going to focus on are going to be the follicular cells. And these are the guys, all right, that make this substance here, this what's called thyroglobulin. You need to know that. All right, thyroglobulin is crucial in the production of our TH, the thyroid hormone. Okay, so it's the follicular cells that make that. And the follicular cells, you saw a slide back in chapter 5 when we talked about glandular epithelium. All right, and glandular epithelium, I'm going to come right back to this slide here. This is what we saw before last semester, or whenever you took 210. All right, in. Okay, here you can see this is the glandular epithelium. These are cuboidal shaped cells. All right, pretty much simple cuboidal epithelium. And at the center, you'll see this stuff here, and that's colloid. Okay, it's a viscous protein substance, and we'll talk about that here in a moment. All right, you can see it a little bit better. Get over here. There we go. You can see it a little bit better on this drawing here. Here's the glandular epithelium. All right, and in the center here, that's going to be our colloid. And the cells themselves these are referred to as the follicular cells. Right, and they're going to be responsible for making thyroid hormone. Okay. All right, let me zip back to that slide. Okay, so understand that those are going to be the predominant cell type in the thyroid. Now, the other cell type, which is important that you know, are the parafollicular cells, all right? And these will not be within the follicles. They'll be scattered in between, all right? And they make this hormone, which you're already familiar with, calcitonin, all right? Calcitonin is going to be the hormone that's going to be produced when your blood calcium levels are high. I don't know why I'm wearing this mask when I can wear this thing and not play with it. All right, so when your blood calcium levels increase, all right, the parafollicular cells are going to release that calcitonin, and that's going to help to lower, we'll talk about this here in a couple slides, that will help to lower your blood calcium levels, all right? And I'll review, we already went over this in 210, all right, but I'll go over it again with you. Okay, so we've already seen this slide, we've seen this slide. I love this slide, it's weird. But a couple things here that this slide really doesn't talk about that I will talk about, all right? And it's only because of the nerdy nature that I have. But this slide here is telling you a little bit of a story of how, all right, we're making thyroid hormone, okay? We'll get into the whole production of thyroid hormone, what causes all that. But a couple players are involved here. Okay, the first one is going to be iodide, okay? So we need that. It's one of the ingredients to make our thyroid hormone. All right, the other substance that we need is thyroglobulin, okay? And it's not listed here, all right, in this picture. And the other one's an amino acid called tyrosine, all right? Tyrosine, tyrosine, okay? That's not as important as iodide, all right, and the thyroglobulin, okay? So basically what's going to happen, this is all going on constantly, all right? So you've got iodine circulating through your bloodstream, okay? Most commonly, we're going to get iodine through our diet, all right? Certain foods are rich in iodine, all right? But perfect example, for those of you that use table salt, common table salt. If you've ever looked, I can't remember what it comes in a blue container, and I don't know what the popular name of that brand for table salt is. It says right on that container. What's it called? Morton. Well, there's Morton. Don't they do the? Oh, I'm confused. I'm thinking Morton's with the kosher salt. Isn't that the kosher salt? It comes in a box. I can't remember. It'll come to me. But anyways, it says right on there, iodized. Okay. They actually. So for most, it used to be an issue way back when. All right, that people were iodide deficient, and so they would get these goiters, which we'll talk about. Okay, that's the thyroid gland having some issues going on because of deficiency in iodine levels. But now, with our diets now, and people putting salt on almost everything, and we always add iodine to the salt, you don't have to worry about it as much, okay? So the iodine gets into your bloodstream, all right, and it circulates around, all right, and it's going to get into the thyroid gland, okay? So you can see here in our little picture, here's our follicle, all right? Now we're just going to zoom in on one of the cells here. Okay, so you have your blood vessel here, okay, and this is actually considered the basilar surface, all right, of a follicular cell, and this is the apical surface. You guys remember that, right? With epithelium, it has this characteristic. It's called polarity. It means that you have a top and a bottom, and then you have sides to it. Okay, so the bottom of our cell, this is the basilar surface. So the iodine enters into the cell through active transport. And it's really cool. This goes back to chapter 4. All right, that active transport process, all right, if you remember what a symport is? It's probably not, because if you took my class, I maybe talked about it for like 20 seconds. All right, a symport is a channel, okay, that will let two things move through the channel, okay? And it can move, the two things can move in opposite directions, all right, or they can move in the same direction. When they move in the same directions, it's symport, okay? Same, easy to remember. So what happens is really cool, because this is an active transport, because there's more iodine inside the cell than outside the cell. So that means the iodine has to go up its concentration gradient, all right? And usually when something has to go up its concentration gradient, it requires energy, ATP. It becomes an active transport process. But the nice thing about this symport mechanism is that that symporter allows sodium to enter into the cell, okay? And if you remember from the nervous tissue, all right, there's more sodium. Some of you haven't had me yet. I said this last semester, banana floating in the ocean, okay? I know, I can even see your expression through your mask, all right? Banana floating in the ocean is a saying that we talk about. All right, what's a banana rich in? Potassium, K+, all right? And then what is ocean water made up of? Salt, sodium, chloride, okay? So when we're looking at cells in general, sodium is going to be in high concentration outside the cell, okay? And so will chloride. But inside the cell, which is our banana, potassium is in higher concentration. So that's where banana floating in the ocean comes from. So sodium is going to want to enter into the cell. Well, that works out for us here because in our follicular cell, as sodium enters in, its movement of entering into the cell creates kinetic energy, because sodium is a charged particle, it's a cation. So that movement of that kinetic energy resultant provides enough energy for iodine to come in also, okay? So the movement of sodium down its concentration gradient helps iodine come in. Even though it's going up its concentration gradient, the movement of that sodium, that kinetic energy, allows iodine to enter into the cell. That's why this is an active transport. You guys got to forgive me, my nose is itchy. Okay. So it enters into the cell. It's got to travel through the cell to the apical surface here. Okay? And so it leaves through diffusion, simple diffusion. Okay, easy to remember because diffusion is moving down your concentration gradient. Okay, so it's going to diffuse across, all right, the plasma membrane here into the lumen here. Now at the same time, all right, these follicular cells are making thyroglobulin. Okay, anything that's made in the rough endoplasmic reticulum, any type of protein, is going to be, it has 3 destinations. Okay, again, I'm going back to chapter 4 on this, and I just got done teaching my 210 class this. It's got 3 destinations. The first destination is it will be proteins that will be embedded into the plasma membrane. So if something needs to be repaired, or if we need to upregulate channels, let's say, maybe we need some more glucose channels to get more glucose into the cell, the rough endoplasmic reticulum will make those proteins. If we need to export proteins out of the cell altogether, okay, like insulin, for example, all right, it will be made in the rough endoplasmic reticulum. And finally, the third destination is this guy right here, the enzymes for our lysosome. Lysosome is this little membrane-bound organelle that goes around and it digests things, okay, amongst other things, all right, but mainly it goes around and digests things, okay? So, all right, our rough endoplasmic reticulum, so what's the point of the iodine? That's right, it is. That's a great question. We have to get our iodine from our blood, all right, into the lumen here. And that's what it does in the beginning. You're absolutely right. It just passes through, Brittany, okay? So we have to get it from the blood, okay, because we just had a salty iodine meal, and now we've digested all that, and it's circulating through our blood, but we've got to get it into the lumen here so we can make thyroid hormone, okay? So it passes through. Once it does that, that thyroglobulin, all right, that was made in the rough endoplasmic reticulum, which is modified and packaged up by the Golgi apparatus, it gets shot into the lumen also. And they both bind together. And how do they bind together? Tyrosine. Tyrosine, there's a peptide bond with tyrosine, and it holds the iodine, all right, to the thyroglobulin. Now, before iodine binds onto the thyroglobulin, you see here, each of these dots is an individual, all right, iodine ion. So what will happen is, all right, these individual iodine ions will team up. So they'll go from just I to I2, okay, which is I gotta look that one up. Diiodotyrosine, all right? I'm mispronouncing that. Hold on one second. No. Anyways, it's two. I'm going to mispronounce it. All right. So what will happen is these 2 iodines will team up. All right. And in some cases, all right, you'll get 2 more that will team up, and then all 4 of them can team up to make a tetraiodine. Okay, 4 iodines. All right. Sometimes you'll get 3 iodines. I'll talk about that in a second. All right. So when all of these team up, all right, the iodine will team up with the thyroglobulin after it's been modified, and it'll turn into, all right, what we call our all right, I'm jumping ahead, sorry. So, all right, this is all in the lumen. All right, I'm going to slow down here. All right, this is where we get our colloid from, okay? The colloid is the iodine molecules along with the tyrosine and the thyroglobulin just sitting out there, okay? So what will happen now is the follicular cell will undergo endocytosis. That's when something is outside the cell and the cell wants it, and it shoots these pseudopods around it and it pulls it in, okay? Endocytosis, remember exocytosis and penocytosis and all that? All right, so what will happen is through endocytosis, all right, this cell will start to pull in that molecule, that thyroglobulin, with the iodine, as displayed right here. Okay? So we call that, all right, that our pre-T3 and our pre-T4, all right, molecules here, all right, are attached onto the thyroglobulin. So what will happen is the lysosome will bond or fuse, all right, to this vesicle, and that lysosome's digestive enzymes will cleave the thyroglobulin completely off of our pre-T3 and our pre-T4, thereby making it just T3 and T4. Okay? So once the thyroglobulin is cleaved off, it is known as T3 and T4. Okay? And when that happens, the cell will then export through simple diffusion T3 and T4. T3 is the active form of the thyroid hormone. Okay? T4, all right, is going to be the inactive form, all right, but it's going to be in greater abundance. So a lot of times, both of these different types, all right, of the T3 and the T4, these molecules are dumped into the bloodstream. T3 is ready to go. T4, all right, is inactive. The cells, when that T4 gets there, it will activate it. Okay, it'll convert it into T3. Okay, a lot of our cells can do that. So when these molecules get exported into the bloodstream, we have carrier proteins, okay, that are circulating in our blood. They pick them up, right? And the purpose for carrier proteins is to help prevent what we call the degradation, the breaking down of certain proteins and molecules. So these carrier proteins will, yes, ma'am. Yeah.
So the tyrosine binds the thyroglobulin and the iodine.
Correct. Yep.
Okay. And then that turns into the pre-T3.
Well, once it enters into the cell, okay, then it has to get endocytosed into the cell, okay? And then what happens is once, right, then it's known as when it's still bound to the thyroglobulin, it's pre-T3, pre-T4, okay? Once it's cleaved off, think of it as we're cleaving off the thyroglobulin, we're also cleaving off off the title of those molecules, all right? So then at that point, then it's just T3, T4, okay? And that's going to be your thyroid hormones. One's active, one's inactive. All right, the active form, the T3, all right, is not in an abundant amount. There's a lot more T4 made, okay? But most of the cells, when that T4 gets to that cell, it will convert it into T3 and then activate it, okay? You got it.
Is there a video on this?
No, there's not a video on this. All right, so knowing now how thyroid hormone is made, there's a lot to it. Don't worry about all the small details. I basically just kind of want you to understand the roles that iodine plays and the role of thyroglobulin and how the iodine gets into the cell and how the molecule is exported from the cell. Okay. So let's talk about what we call the hypothalamic pituitary thyroid axis. Okay. So when we look at the name here, hypothalamic means we're going to be dealing with the hypothalamus, and then obviously pituitary, and then the thyroid. Those are all the players involved here. That's what this picture represents. All right, this is the hypothalamic pituitary thyroid axis. All right, that's what all this is basically representing. Okay, so let's start off with what is the stimulus? All right, what causes the eventual release of our thyroid hormone? All right, cold temperature. I have a theory that gyms, when people go and work out at them, if they keep their temperatures lower, I'm not saying freezing cold, all right, but not at 70 or 72 degrees, maybe around 66, even maybe 68 degrees, that lower temperature will increase people's metabolism. Is there a way to prove that? No, it's just a theory, all right? But, all right, people, when they go to work out, they want to increase their metabolism. What a nice way to do that, by putting somebody into a cold environment. So cold temperature is one of the stimuli. All right, pregnancy, because remember, when mom is pregnant, all right, her metabolism is kicking up because a lot of changes are going on in the body. A lot of things need to be prepared for baby, okay? High altitude, okay? So folks that live in the Andes Mountains in South America, or the Himalayas, or even on our Rocky Mountains, all right, those high altitude folks are going to be producing more thyroid hormone. Hypoglycemia, what's that? That's right, low blood sugar, okay? Thyroid hormone, all right, will help increase your blood glucose levels. All right, and then obviously low thyroid hormone. Remember the negative feedback system. Okay, if you're low on something, it's going to trigger that stimulus will trigger the opposite effect, so we're going to increase it. Okay, so all this is going to stimulate, all right, your hypothalamus to release thyroid releasing hormone. Okay, remember your hypothalamus is a regulatory structure. All right, it's either going to release or secrete a releasing hormone or an inhibiting hormone. In this case, it's going to be secreting a releasing hormone. So TRH will then stimulate the anterior pituitary or the adrenal hypophysis to release its thyroid stimulating hormone. And then thyroid stimulating hormone is going to bind onto the receptors for the follicular cells, and then it's going to trigger the release of thyroid hormone. Pretty good? You guys see that pattern? We're going to see this same kind of pattern. If you're getting bored with it, that's a good sign, because that means that, all right, we already know what's going on now, okay? So this is what I was talking about here with our T3 and our T4, because those follicular cells will release that T3 and T4 into the bloodstream, okay? So we got the triiodothyronine and the tetraiodothyronine, all right, the T4, all right? And these, once they're released into the blood, they will immediately bind onto the carrier molecules. Here's the thing. Not all of it binds onto a carrier molecule, okay? So some is going to be free floating. Just know that if it's not bound to a carrier molecule, it better get absorbed by a cell quickly, or it's going to start to be degraded, right? It just starts to break down, okay? All right. So that's what this picture here is. I'm just going to go over it real quick. Okay, here you can see, here's our stimulus, all right? So we have the negative feedback system, the decreased thyroid hormone being produced, or cold weather, high altitude, pregnancy, all right, hypoglycemia, yada, yada. All right, the hypothalamus detects that, all right, which then it releases its TRH into the to the portal system there, all right, the hypothalamic adrenal portal blood system between the two, all right, between the anterior pituitary and the hypothalamus. The anterior pituitary then releases its thyroid stimulating hormone onto the thyroid gland, okay? And that will then stimulate the thyroid follicular cells to release thyroid hormone. So what does the thyroid hormone do? Keep in mind, overall, all right, overall, it's going to increase cells' metabolism, okay? So it's going to increase cells' metabolism. So, okay, when we're talking about cells, especially the neurons, they're going to increase glucose uptake, because remember, the brain, keep in mind, always, 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 the brain loves glucose. It's a sugar fiend. It has to have its glucose. It gets priority to glucose, all right? So, same with you? You're a sugar fiend? I had so much sugar this weekend, I don't even want to get into it. So what we're going to see here is those neurons are going to get top billing for it. So you can see in our diagram here, all right, glucose is going to be absorbed from the bloodstream into these cells, but specifically the neurons. So how do we get glucose in the bloodstream? We should know by now how we do that. And if not, no worries, because by the end of today, you will know. You won't even have, I hope you won't have to memorize it. Our liver, okay? Our liver is going to start to break down glycogen, okay? We call that process glycogenolysis, all right? And then if we don't have enough glycogen stored, well, we're going to start making our own new form of glucose from non-carbohydrate sources. And that process is called gluconeogenesis. Amino acids, fatty acids, lactic acid, all that stuff we're going to use to make glucose. And guess what organ does it? The liver, okay? So we're going to try to increase our blood sugar levels, okay? Hence, if we're hypoglycemic, this works out great for us, okay? So keto is a different one, because and a lot of times you're basically kind of forcing into a specific type of metabolism with ketone bodies. And that's an important aspect, because there's a difference. People get that confused. Ketone body metabolism and ketoacidosis. They're different things. They both have keto in them. All right, ketoacidosis is bad. That's when you get somebody with diabetes and they've used up and burnt up all their sugar sources. And now they go into ketoacidosis, increasing their blood pH. And that's a problem. Because when you start to increase blood pH, you start to break down proteins. When you start to break down proteins, you're going to ruin enzymes. You're going to ruin the proteins in your plasma membrane. All right, so those channels that you value, they go away. Okay, causes problems. But ketone bodies is a good energy source in certain regards. So your brain, if it uses up all the glucose, it'll start to utilize ketone bodies. So basically, with the keto diet, you're basically taking away. It's like if a kid's very hungry, if you put a donut in front of them or if you put broccoli in front of them, most times they'll go after the donut. Now take the donut away and just give them broccoli. They're starving. They're going to eat that broccoli. And that's what's going to happen. All right, that's pretty much what will happen with your brain. You give it one energy source, it'll utilize it. If you give your cells one potential energy source, they'll have to use it. Yeah. So we're going to see, all right, a decrease in glycogenesis. No, excuse me, in glycogenesis. Okay, we're gonna stop making glycogen. Okay, we want to get that glycogen into the bloodstream because we want to elevate our blood sugar levels. All right, same thing with the adipose cells. They're going to break down the fats and release the fats out into your bloodstream. So the glycerol molecule and the fatty acids will go into your bloodstream. Now, while all this is going on, all right, you see here in the lungs and your heart, you get an increased breathing rate. Why do you think that is? I'm going to try to hide this because it says the answer right there. Why do you think your breathing rate increases with thyroid hormone? Exactly. Aerobic respiration, you want to get oxygen because most likely if you're increasing your metabolism, you're probably doing something active, exercising, or you're in a stressful situation, or it's just at that point in puberty, your metabolism is just kicking in really hard and it's just working as you're growing. Okay? So we want to maximize that. We want to increase our oxygen intake so your respiratory rate increases. So you're going to be blowing off more carbon dioxide, but breathing in more oxygen. And we need oxygen for that aerobic cellular respiration. Okay? So at the same time, too, your heart rate increases. Okay? And your heart rate increases because, and not just your heart rate going from, let's say, 50 beats a minute to 80 beats a minute. Okay? But also the force of contraction. So you're going to pump more blood through your circulatory system, all right, more efficiently, and you'll have more because we got to get that oxygen to the tissues that need it. Okay, so all this has to do with, all right, trying to meet the increased oxygen demand by those tissues. Okay. So stress stimulates the thyroid gland to release thyroid hormone. Well, see, stress is a general term. Now, see, this type of stress that you might say, like, hey, I'm stressed today. That's more of a psychological stress. I'm talking about more of a mechanical body stress. All right, cold temperatures is going to be a stressor, so that's going to cause the metabolism to increase. All right, so you can see here in our diagram, see the liver is pumping out all this glucose into the blood, but meanwhile, all the cells in your neurons are sucking that glucose up because they need it. All right, and you can't, there's no arrow here, but as your adipose cells start to break down the lipids and they pumps glycerol fatty acids into the blood, that glycerol fatty acids are going to go into the liver because of gluconeogenesis. Okay, so we're increasing our supply for stuff. Okay. All right. All right. So here we're talking about thyroid hormone. All right. And basically how it works is it circulates through your blood and it's going to then find a receptor, and there's pretty much receptors on pretty much all the cells in your body. Okay. And then what will happen is, all right, in some situations, all right, the cell, if it's the T3, it's the active form. Nothing else has to be done. All right. But the T4, all right, is not. So when that binds onto the receptor, the cell itself will then convert the T4 into T3. Okay? Which is ideal. Now we don't have to worry about having all this inactive thyroid hormone floating around. All right? So basically, all right, when we increase metabolism in our bodies, in our cells, all right, our cells are going to be doing things, making energy, or if it's a cell that's supposed to make something, all right, pretty much if they're making something, they're making proteins. Okay? Proteins are very abundant in our bodies. So when that occurs, all right, when we're dealing with neurons, we might want to insert more sodium potassium ion pumps into our plasma membrane. Why is that important? What do sodium potassium ion pumps do? This is back from chapter 12. They help to maintain the electrochemical gradient of the neuron. Okay? Because remember, 2/3 of the energy expenditure of a neuron, all right, is from the operation of those sodium potassium ion pumps. So we have more in the membrane, we have more pumps working, all right, that helps to lower, all right, the workload. Okay? It's like having, if you're moving, would you rather have 2 people helping you move your house or 10 people? Right? Same thing. Okay? So that's what we're going to do here. While all that's going on, just like if you're actively walking or doing whatever, all right, anytime you have a chemical reaction, now I'm getting into chemistry here and a little bit of biochemistry, and I won't linger here very long. But you have basically biochemistry or any type of chemical reaction in your body, all right? You're changing something from one thing to another thing, or you're breaking something down. That requires chemical reactions in your body, okay? And as a result, all right, with some chemical reactions, a byproduct of that chemical reaction is heat. So you'll start to heat up. And that's where this term comes from, okay? Calorogenic, okay? When you're working out, you're breaking down those energy stores, all right, and it generates heat, aside from other things that are going on, all right? But keep that in mind, all right? So I talked about with protein synthesis, what is the building block for proteins? Amino acids. So where can we get our amino acids from? Okay, we'll get those, all right, when we break down some of our fats, all right. Amino acids are great for that, okay. So we're going to want to increase our glucose uptake too to help supply energy for these cells, okay. And then we'll also see, all right, our mitochondria kick it up a notch because oxygen is pretty prevalent because we've increased our heart rates and our force of contraction, but also our breathing rate. So oxygen is readily available. Mitochondria need that oxygen to undergo cellular respiration, okay? So what will happen is, all right, the actual mitochondria will start to increase the cellular respiration enzymes for, we'll talk more about this in later chapters near the end of the semester, all right, we get into the Krebs cycle, the TCA, the tricyclic acid cycle, all right? We'll talk about the enzymes that are involved with cellular respiration. All right, but at this point, just know that we're going to increase the number of cellular respiration enzymes. Okay. So think about this. When you're increasing the metabolism, think of the big picture, and then we can go down into the more specifics. All right. Thyroid hormone, we want to increase our ATP production. Okay. So the liver, all right, is going to break down glycogen, pump it out into the bloodstream. It's going to utilize gluconeogenesis to make more glucose to pump out into the bloodstream, all right? As that is going on, it is going to stop making glycogen, okay? And that will keep your blood sugar levels elevated, okay? So as that glucose is circulating through your bloodstream, it's readily available for the cells that are now undergoing an increase in metabolism. All right, your adipose cells, I talked about this, all right, they're going to break down fats into glycerol and fatty acids, so we can use those glycerol and fatty acids for energy production, okay? And by doing that, all right, we're allowing, glucose to be saved for the brain. And there's the name of that is the glucose sparing effect. Okay? And then these last two I already talked about, all right? Increasing respiration rate so we get more oxygen for our chemical reactions, and then increase our heart rate and the force of contraction, because now we want to give all that glucose that's circulating through the blood and that oxygen, we want to circulate it throughout the body so those cells that are undergoing the increased metabolism have enough energy and oxygen to make that ATP. Okay, that's our goal. ATP, we need it. Sounds like a lot, but that's what's going on. All right. And one of the things too, and we talked about this a little bit in 210 about epinephrine and norepinephrine, nicknamed adrenaline. Okay, adrenaline, when your adrenaline kicks off, your heart rate increases. All right. So this is something here. All right, with thyroid hormone. Okay, it's going to upregulate. All right, the receptors on your heart for norepinephrine and epinephrine. Specifically, when you have a fight or flight response. All right, when you're running for your life, let's say, okay? So we want to make sure that when that adrenal medulla is secreting epinephrine and norepinephrine, right, when it circulates through your circulatory system and winds up in your heart, that there's plenty of receptors to increase your heart rate, increase your force of contraction, okay? Keep wanting to go for my water, but it's empty. I learned a lesson. Dehydrate yourself when you ever have to do a long drive. That way you take fewer pee breaks. Just saying. It's not a good idea? Well, when you don't want to keep stopping. Normally it takes me about 12 to 13 hours to drive up to New York. 1 year it took me 16 hours. And it's because I was the driver. I had my brother-in-law's dog with me. Don't ask me why. I had to bring his dog up to New York. And then my 2 kids. And we couldn't time pee breaks, gas breaks, and then food stops. So what normally would take me about 12, 13 hours took me 16. Will not do that again. All right. So let's talk about a couple disorders of thyroid hormone. All right. Hyperthyroidism. You don't hear as much about it as you do with hypothyroidism. Obviously, we talk about hyper, or we have too much thyroid hormone. Okay. And so what we'll see when you're producing that too much thyroid hormone, all right, you're going to see your metabolism take right off. Okay. So what happens is there's an experienced weight loss. Why? Because you're constantly releasing nutrients into the bloodstream. Those nutrients are being used by the cell for metabolism. So you're not storing fat. You're not storing sugars. You don't have time to accumulate things. So you start to lose weight. All right, you have all this energy because your blood sugar levels are constantly circulating through, and your cells are constantly utilizing that, constantly secreting norepinephrine, epinephrine because of the upregulation of your heart rate and force of contraction there. All right, and you can't handle the heat, so you got to get out of the kitchen. Okay, because what's going on? Your metabolism is constantly going and going and going. You're constantly having these chemical reactions occurring. And what's the byproduct? Like I said, heat. All right, we call those exothermic reactions. The byproduct is heat. Okay? So this could be caused by too much, all right, T4, all right? Or your pituitary gland can be constantly stimulated. All right? Whether it's from the hypothalamus or maybe there's a tumor. A pituitary adenoma could cause that, a growth on the pituitary gland, which stimulates the release of TSH, thyroid stimulating hormone. Okay, you've seen it before. All right, or we just destroy our negative feedback system. Okay, and the saying is, all right, when we have that loss of negative feedback, all right, on the thyroid gland, that's called Graves' disease. Easy way to remember that is, if you lose that negative feedback, it's going to put you in the grave. I don't know. Someone told me that once, so I just remembered it. Okay? So how do we treat this? Take away the culprit that's causing this. Get rid of the thyroid gland. Take it out, and then just give people thyroid hormone. Okay? Oh, why? This is awful. Guys, and again, it's not an excuse. I'm only operating on about 3.5 hours of sleep, and so my ability to recall things is a little bit limited right now, but I'm trying to remember the thyroid hormone medication. Thank you. Thank you. I cannot remember Synthroid. I don't know why. I mean, I see it all the time. All right. The other type, all right, of a disorder with thyroid is hypothyroidism. So this is the person, we see this much more frequently. All right. 2 of my family members have it. All right, specifically my mom has Hashimoto's. All right, but in this situation, people that are suffering from hypothyroidism are going to have low metabolism, okay, because they're not producing that thyroid hormone. All right, so when that happens, all right, they're going to have weight gain occurring. And again, they're not going to have all that energy, nutrients being circulating throughout the body, so they're going to get tired, okay? And they can't handle the cold very well, okay? So these people are constantly cold.
I wish that was the reason.
They're constantly cold, all right? So in this situation, this is caused by decreased iodine, okay? If you have a decreased iodine, you can't make thyroid hormone. Easy enough, all right? The pituitary gland is not getting stimulated. Maybe the hypothalamus is not producing enough thyroid releasing hormone to stimulate the pituitary gland, all right? Maybe by accident, you were having a surgery on one of the structures in your neck and the surgeon messed up and destroyed your thyroid gland. Could be an issue, all right? Also, and this last one here, immune system destruction of the thyroid, that's Hashimoto's. That's what my mother has. She actually has antibodies that her body actually makes, and it literally attacks the thyroid gland, destroying the receptors and whatnot. So therefore, she takes Synthroid. Okay? So what do? Take thyroid hormone.
So the same medications for both?
Well, not for both, but the treatment for hyperthyroidism is to get rid of the gland. Once you do that, then you're not making thyroid hormone anymore. So as a result, you do have to give them some thyroid hormone. Yeah. In some cases, and it's not even listed up here, you can, for the hyperthyroidism, you can blast the thyroid gland with radiation too. That was an older method that they used to use. They don't use it so much anymore. But they, because more people are kind of freaky about excessive x-rays, you know, which I don't blame them. Yeah, I don't want to glow in the dark either. Pardon?
People love prescriptions.
They do, you know, drugs are king. All right. Goiter, this is that big lump in your throat, all right? This is what happens, all right, when you do not have enough iodine, okay? So when you don't have enough iodine, all right, then what happens is your, think about the negative feedback system, all right, that hypothalamic pituitary thyroid axis, right? You don't have enough iodine, you can't make thyroid hormone. Thyroid hormones are low in the blood. So when that blood flows up to the hypothalamus, it's like, wait a minute, there's not enough thyroid hormone. Let me release more TRH, all right, which stimulates the adenohypophysis or the anterior pituitary to release thyroid stimulating hormone. Guess what? Thyroid stimulating hormone goes to the thyroid gland, but we don't have iodine to make thyroid. Right, but we're still stimulating the gland. The gland just gets bigger and bigger and bigger, okay? And it's all because we don't have enough of this. So somebody that's much smarter than me came up with the idea of just putting it in our salt, and voila, we good.
But definitely not common to do that anymore.
Not so much, no. And if you if it is, if you do see people with it, there's usually some sort of issue with their diet. So it's a personal cause. It can't. Yeah, it used to be. I mean, it used to be big back in the early part of the 19th century. All right, but ever since my lifetime, you very rarely. Now, if you travel to other countries, maybe. All right, and especially if there's not iodine in some of their meals that they eat. All right, wherever they get their food from. All right, and they're not supplementing, then you'll see goiters in certain societies. Yeah, Lugolf's. Not Lugolf. Hold on. It's so similar to Lugolf, but it's an actual. You can actually go to a pharmacy and buy liquid iodine and drink it. Oh yeah, it's in certain foods. Yeah. Right. Yeah, there's certain, and I'm trying to think of the vegetables off the top of my head, and I can't recall, which is awful. I'm having a bad recall day. All right, let's wrap up the thyroid gland with, all right, the parafollicular cells, the other cell in the thyroid, okay? These guys make calcitonin, Okay, and we'll see calcitonin in situations in which you have high blood calcium or stress from exercise. Why do you think that is? You ever wonder? Well, probably. I do. But why do you think, all right, stress from exercise will increase calcium floating through your body? Right, mechanical stress on the bones will cause bone remodeling. And that bone remodeling will stimulate osteoclasts. And osteoclasts break down the bone matrix, and in that process, they release calcium into the blood. You nailed it. Good. You had an awesome teacher. All right, so that's what we're going to see here. So now what's going to happen with calcitonin is calcium is going to put, calcitonin, that hormone is going to put calcium, all right, that's floating in the blood into tissues, all right? So one way that it's going to decrease calcium being released from, all right, bones is eliminate the culprit, okay? Stop osteoclasts from breaking down the bone matrix, okay? So we stop them, then they can't break the bone matrix down. And at the same time as we do that, we tell the kidneys, yo, get rid of calcium. So the kidneys now are going to start peeing out calcium. And that will drop because, as you know, the kidneys filter your blood. So as we're filtering the blood, we're going to filter out the calcium and you pee it out. Okay? That's calcitonin. All right. We saw this slide. I'm going to kind of move through these next couple of slides here relatively quickly because we saw this in lab. All right. Adrenal glands. Let's move on to the adrenals. Okay? Keep in mind the position of the adrenal glands. They sit on top of the kidneys, all right, and the kidneys are superior to the kidneys, and the kidneys are a retroperitoneal organ, which means they sit behind the peritoneum. And the peritoneum is a serous membrane, all right, that lines your abdomen, okay, and these sit behind it. It's important to know, especially when you have internal bleeding going on, okay? So these tissues and organs will sit in fat. And what's one of the purposes of fat or functions of fat? Insulation, cushioning, okay? And that's one of the reasons why when we talk about certain eating disorders like bulimia, anorexia nervosa, those folks have such reduced body fat that it's so dangerously low that their organs literally, when they bump into each other, can damage each other. All right, because their body fat has gotten so low that the fat that would normally be around these organs is no longer there, or it's no longer there in high amounts, and it can cause issues. Okay, so there's two parts or two regions. Okay, the adrenal medulla, which is the inner portion. Okay, and this is the part that produces epinephrine and norepinephrine. And you need to know this. It's released through the sympathetic nervous system, that fight or flight. You have a direct neuron connection from your spinal cord all the way to the adrenal medulla. Okay, most neurons will synapse at least once by the time they get to their effector organ. This pathway, nothing. It passes through ganglions, but it doesn't synapse there. That's important to know. Because remember, synapses slow down nerve signals. Because remember, you go to a chemical synapse, then it takes time to convert that electrical signal into a chemical signal as we release the neurotransmitter. Doesn't seem like much, but it is a slowdown. But if you don't have any synapses, it's a direct line, okay? The other part of the adrenal glands is the cortex. This is the outside, all right? And so the outside pretty much is going to produce these corticosteroids here. It appears yellow because of that high lipid content. Because remember, when we're dealing with steroids, all right, one of the precursors for a steroid, you remember the molecule? Cholesterol. All right, we need cholesterol. It's a precursor. It's one of the ingredients for our hormones and steroids, okay? So there's three regions or layers. You probably remember this from last week. The zona glomerulosa, that's the most superficial. Then we have the zona fasciculata, that's the middle layer. And then we have the innermost layer, that's the zona reticularis. That's where I gave you the GFR, all right, the glomerular filtration rate that comes from the kidneys, okay? All right, so here we saw this last week, all right? Here are the kidneys, and right on top, all right, you can see the adrenal glands. And they'll have a yellowish appearance to them. All right, again, we saw this last week. All right, the outer, keep in mind, the outer covering to the adrenal gland and the kidney has a capsule, okay? And that capsule is made up of what type of connective tissue? Dense irregular. Yep, dense irregular connective tissue, okay? So that coats, all right, the adrenal gland. And then just internal to that, we have the cortex. That's this outer layer here. Okay, and the cortex has these 3 layers, all right, inside. All right, the zona glomerulosa, the zona fasciculata, and then the zona reticularis. And then the innermost layer, that's the medulla. All right, and the medulla is where your epinephrine and norepinephrine are made. Okay. All right, so this slide should look familiar to you too. Let's talk quickly about what hormones are made in the cortex there. Okay, so in the zona glomerulosa, our mineral corticoids are produced there. This is where I asked you last time. Hopefully you remember. What's an electrolyte? Booyah! Someone was listening to me. I know you all were. I know you all were. Because no one has fallen asleep on me yet. All right. I'm afraid to tell you, I don't want you to think less of me, but I was that person that would fall asleep in class. And it's only because I was up till like 4 in the morning studying. That was my own fault. But, oh, yeah, it was. Yeah, it was. I did my best studying late at night. Does anyone else do their best studying like late? Yeah. Oh, yeah. Well, when I was young and single, I didn't have a family, I could do whatever I wanted. It was much easier to get away with that. All right. Yeah, you sleep. Yeah. So for me, yeah, see, I could see, yeah, Brittany, it's one of those.
Probably could get up at 6:30.
That was my cousin. I've got a cousin, no matter what, he is up every day at 6:30. He could go to bed at 4 in the morning, he's up at 6:30. I mean, I'm jealous of him. Yeah, I mean, I would love to be able to get by on that. All right, so the zona glomerulosa is going to be the part of the adrenal glands that's going to make the mineral corticoids here. All right, specifically aldosterone. Okay, you want to know the function of aldosterone. It is going to not secrete, but it's going to reabsorb or what's the word I want to use? Well, resorb, hold on to sodium. Okay, and it's going to get rid of potassium. Now remember, water is, how do I want to say this the right way? I was going to say water is weak. It's not really weak, but it's like, yeah, water follows. It's a follower. Okay, water likes to follow sodium wherever it goes, and it likes to follow sugar wherever it goes. And we talked about this last week too when we were talking about diabetes. All right, you have a lot of sugar in your urine, then the water will follow the glucose into the urine and pee it out. That's why people with diabetes have to pee all the time. All right, in this situation, aldosterone is going to retain sodium, so therefore it's going to retain water. So prevent you from being dehydrated. So when you start to enter a dehydrated state, all right, your adrenal glands will start to increase the production of aldosterone so you can retain water more, okay? And it does that because you retain sodium, okay? All right, the next type of hormone are your glucocorticoids. All right, that's cortisol, that's the stress hormone, okay? So cortisol, all right, is going to increase your blood sugar. So it's an antagonist, all right, of insulin, okay? You know, the insulin is the only hormone in your body that does what it does. All right, you got like 10 hormones that are antagonistic of insulin. Growth hormone is one, cortisol is another. All right, but like insulin is, that's why people with diabetes, they're so debilitated, because you don't have like a backup hormone that could fall back onto what insulin does. Some can do like one thing that insulin does, but there's not a single hormone that does everything that insulin does. Okay. So cortisol will increase your blood sugar level, which makes sense, right? If you're in a stressful situation, all right, if you're going to go work out, let's say, or you know, you're being chased, all right, down an alley by a car, all right, you need to outrun this car, all right, your insulin, your blood sugar levels will increase through the release of cortisol, because think about it, all your cells need that glucose for the purposes of energy production, ATP, okay? So cortisol is going to increase blood sugar levels. So it absorbs to the sodium. Well, don't think of, Brittany, don't think, when you say it, are you referring to water? Water is attracted to sodium. Okay, what do you mean? Are you saying like the kidneys will absorb sodium? Aldosterone, I see what you're saying, yeah. So what will happen is aldosterone, all right, when it gets produced, okay, it will then stimulate, and we'll talk more about this when we get into renal physiology, it will stimulate the kidneys, all right, to what we call resorb, all right, sodium, all right, and therefore it will filter out potassium and excrete it through the urine, but it saves and holds on to the sodium. You won't pee out the sodium. You'll keep it in your blood. Okay? And then finally, the gonadotropins, those are the sex hormones, all right, made by the zona reticularis, all right? And the male sex hormones are what we call androgens, okay? And the androgens, all right, are going to be made by the adrenal glands. In women, all right, you convert the androgens into estrogen. I think I talked about this last week about hirsutism, okay? And hirsutism is when the female is unable to convert the androgens, all right, into estrogen, and so they'll have elevated testosterone, which will give them some masculine features, okay? All right, so how do we regulate cortisol? Okay, our stress hormone, all right? So keep in mind, all right, cortisol and corticosterone, okay, are going to increase the nutrient levels in our blood, okay? We've got to get the stuff that's sitting in the cells out into the blood, so the much needed cells, like your muscle cells, all right, for exercise or whatever, can use those nutrients for energy production, ATP production, okay? So when we get cortisol and corticosterone released into our blood, all right, this will help with, one, injured tissue, all right, and that's why if you get a cortisone shot, all right, in damaged tissue, the reason why is to deal with inflammation. Okay, inflammation is part of the natural healing process. You want inflammation. You don't want excessive inflammation. Did I say information? Inflammation. I know. I'm probably giving you excessive information. All right. So to understand that, all right, again, do you guys kind of feel like you understand the pattern that we're going to embark here when we talk about the hypothalamic pituitary blank axis? All right, it all starts with the hypothalamus. All right, that's where the receptors are. All right, so again, what we'll see here, and I'll show you this picture, I'll come right back to this slide here. All right, we're always going to start here with the hypothalamus, at least for these hormones that we've covered so far and a few more. It's going to change here in a bit when we get into the pancreas, when we talk about insulin and glucagon. All right, so keep in mind, this same pattern is going to occur. So what is going to cause, all right, what are some of the stimuli? Obviously, like I said, stress, all right? Remember how growth hormone was affected by sleep, all right, certain times of the day or night? Growth hormone is going to be released, all right, in high concentrations and low concentrations, depending on what time of day it is. Same thing here, all right, with cortisol, all right? And in fact, growth hormone and cortisol have almost opposite release patterns, okay? When one is high, the other is low, all right? So late stages of sleep, all right, will release cortisol. When we're talking about growth hormone, it's going to be the early stages of sleep. That's why you should never feel bad, and you should never feel bad when you send your kids to bed hungry. I'm going to tell you why, all right, real quick, all right, and then we can take a break here in a moment, all right? It's not bad to send your children to sleep hungry, okay? And the reason why is when if you feed your kids, and I got into my good friend, she's a neighbor down the street, she used to let her kids eat like Fruity Pebbles and Fruit Loops right before bed. You know, and in the summertime, she lets them go to bed a little bit later. They're young. Well, they're 10 and 7. And she would let them go to bed around 11 o'clock at night, okay, in the summer. Not all the time. And she would give them this food. So what happens when you eat a very sugary meal? What happens to your blood sugar levels? They increase. So what happens if you have high blood sugar levels? What gets released? Insulin. Insulin level, all right? So when insulin's being released, all right, insulin is antagonistic of growth hormone. So when insulin levels are high, when they shouldn't be, all right, your insulin levels shouldn't be high when you're a little kid at 11 o'clock at night, all right, or at midnight, okay? When insulin levels are high, growth hormone levels will be suppressed, okay? That's why you should eat when you're younger, if possible, around 6, 7, latest 8. All right, because then insulin levels will drop back down, and then when it's bedtime, your growth hormone levels start to spike. All right, so what she was doing, all right, is she was giving her kids these Fruity Pebbles, and they're going to bed, and their insulin levels were spiked well into the time that the growth hormone levels would be spiked. So I had to sit down and teach endocrine physiology to her daughters, so they could go back and explain it to mommy. And they did. And it's funny. I mean, I had, at the time, her oldest was 9, and she went and explained what I'm teaching to you. All right. Now, obviously, in a little bit more simple terms, but she was able to explain to her mom. Yeah, and she's right. Yeah, exactly. And she said, and her daughters convinced her mom to stop feeding them garbage before they went to bed. All right. Anyways, I know, exactly. I would love Fruity Pebbles. That's my favorite. And then, so same type of pattern going on here.
What about for adults?
Fruity Pebbles?
Can we eat those at night?
No, you should actually eat the box. There's more nutrients in the box of Fruity Pebbles than Fruity Pebbles themselves. All right? But it's by far my favorite. See, I grew up in a house where my parents wouldn't let us have sugared cereal. So yeah, we weren't. I mean, to us, a sugared cereal treat was, I think, Kix. You know, there wasn't much sugar, if any, in that. Yeah, exactly. I mean, it was a big treat. We got Raisin Bran. You know? Oh, I know. I'm telling you.
I hate all brands.
Yeah. All right. So, starting off here, honeycombs. It's so funny you say that. Honeycombs was another one. We knew we did something right if we were eating honeycombs. That was really a treat for us. Yeah, exactly. Just bring me Fruity Pebbles because you like me. I love Fruity Pebbles. All right. Hypothalamus. When there are stressful situations, when you're in the late stages of sleep, or when you have low cortisol, the negative feedback loop, okay? When that occurs, your hypothalamus releases, all right, CRH, which will then stimulate, all right, the anterior pituitary, again, to release adrenocorticotropic hormone. All right, ACTH then is going to stimulate the release of cortisol and corticosteroid. Okay, so that's what this slide is going to show you. I'll come back to that slide in one moment. That's what this slide is showing us here. Okay, what I just said in words. All right, negative feedback loop, time of day, and stress will cause the release of the corticotropin releasing hormone from the hypothalamus, which will then stimulate the adrenal corticotropic hormone, or ACTH, from the anterior pituitary down into the adrenal gland here, all right, thus stimulating the release of cortisol. What will happen? Let me go back one slide. I have a tendency to skip around here. Let me go back and finish this slide up for you folks. All right. Once cortisol is released, it's going to travel through the blood, and guess what? It uses carrier proteins, okay, which is good, right? Because what happens with carrier proteins? They prolong the life of the hormone, which is what we want, especially when we're in a stressful situation. It does not make sense if the half-life for a hormone, let's just make up a number, is 5 seconds, right? When it's on its own, if the half-life is 5 seconds, it'll go away real fast. But when it's attached to carrier proteins, it prolongs the half-life, so they don't degrade. So the effects will last longer, okay? So some will pop off of the carrier protein and go into the cells. And then we're going to talk about the effects here in a moment here, all right? So going down here to our cells, all right, what's the overall effect of cortisol? Increase blood sugar levels. So I don't even have to probably pull this up for us to figure out some of the organs that are going to take a role in that. Do you think the liver is going to do something? How does the liver increase blood sugar levels? Yeah, it breaks down glycogen. Yeah, it'll break down the glycogen. So we have glycogenolysis. Okay, we break down the glycogen and it increases gluconeogenesis. All right, so our liver, all right, look at it right here. Boom, increase glycogenolysis and gluconeogenesis, while at the same time I'm rushing here, let me slow down. At the same time, it decreases or inhibits, all right, glycogenesis. Golly, I cannot talk today. I'm so sorry, y'all. All right. So when the liver is pumping out glucose here into the bloodstream, all right, for all the cells in your body, all right, to utilize, all right, but more importantly, it pumps out glucose into the bloodstream so your brain gets first dibs. Again, we're going to see that glucose sparing effect. All right. Our fat cells, again, are going to break down fats, so lipolysis, and it's going to decrease the creation of lipids. All right, so it's going to decrease lipogenesis. All right, now here's something new that we haven't seen before. All right, our cells in our body are going to stimulate protein catabolism. Okay, breaking down of proteins. Okay, normally we've seen the cells will utilize increased glucose uptake, but these cells are going to break down, all right, proteins. Why? What do we get when we break down proteins? What's the building block for proteins? Amino acids. Yeah. So these cells are breaking down proteins into amino acids. All right. Guess what? Now we have another source for our liver to make glucose through gluconeogenesis. Okay. And we'll talk about the high doses here in a second. All right, I got another slide for that. All right, here's that picture here. And if you look way back here in the beginning of this chapter, there is a slide that shows growth hormone, and it's almost the opposite of this. All right. Well, that's a horrible kind of drawing there. It kind of goes up. It's earlier on in my slides, and it's also in your chapter. All right, but growth hormone and cortisol are almost opposite there. All right, so basically what I was just showing you there, just a quick review here. All right, the effects of cortisol. All right, so when we talk about the target cells, our overall goal is to increase blood nutrient levels. All right, so what's the liver do? It's going to increase nutrient levels of glucose. All right, through glycogenolysis and gluconeogenesis. Adipose cells are going to increase glycerol and fatty acids through lipolysis. All right, and then the body cells are going to break down our proteins and give us our amino acids, which is one of the building blocks for glucose through the process of gluconeogenesis. Okay. And by doing that, then all that glucose, like the liver has given us, all right, goes to big brain, okay, with the glucose sparing effect. All right, one more slide, and then I promise you we'll take a break. Great question. We're gonna talk about that. Yep. I love it when you guys are thinking ahead of me. Do you know somebody with Cushing's disease or?
No, yet my dog.
No. It's crazy. I had a cat that had hyperthyroidism, and then she burnt out her thyroid, and she ended up eventually getting hypothyroidism. And they wanted to put her on steroids and all this. She was about 20 years old, and I was like, I'm not gonna let her live like that. You know, I mean, she was old. Good cat, awesome cat. Huh? Oh, that's right. All right, let me wrap up with this slide here. All right. When we talk about the corticosterone, And when you hear about people getting a steroid shot, all right, this is what they're referring to, okay? And this hormone is great for inflammation. And the reason why is because it prevents phospholipase A2. We talked about that at the beginning of this chapter. All right, that's that enzyme that breaks down arachidonic acid, which is one of the amino acids in the phospholipid bilayer of your cells. Okay, this amino acid starts that enzyme cascade, and we get prostaglandins, prostacyclins, leukotrienes, all those little fun, eicosanoids that are great for pain and inflammation. Well, guess what? This, stops it right in the beginning. It stops that enzymatic cascade right at the beginning. That's why steroids are wonderful. But unfortunately, continual use of steroids, will impede the immune system, which is not good, and it can also cause your bone density to decrease. Okay? Yeah, that's not good either. Okay? So it suppresses the immune system. Yeah, it's great that it inhibits inflammation. All right? That's why it's good to use a steroid shot a couple times. But if you're getting a weekly or monthly steroid shot for many, many years, you're going to have problems. Okay? So because it reduces or suppresses your immune system, you're more at risk for cancer, infections. All right? You're also going to see increased retention of sodium and therefore water, so people look more puffy, right? Anxiety, they get more cranky, all right? And this is important too, it inhibits connective tissue repair, all right? So if you were to damage tissue, it's much more difficult to repair that tissue. So why do athletes use steroids? That's a great question. And that gets into anabolic steroids. See, catabolic steroids are the type of steroid, which is what this is, that breaks proteins down. We just saw that. Remember right here on this slide? Oh my Lord, there it is. This is what a catabolic steroid does. All right, that causes cells to break proteins down. Anabolic steroids build proteins up. Okay, so you'll start off with a bunch of amino acids, and then anabolic steroids will help to build those amino acids into proteins, where catabolic steroids start off with a protein and tear them down into amino acids. So athletes that use steroids, that type of steroid doesn't affect the bone as much. They have to worry more about blood clots, right? I saw a video on a guy that was